So in this video, we're looking at the SEC 2013 Leaving Cert Higher Level Maths Paper 1, Question 1. And it says Z is equal to 4 over 1 plus root 3i is a complex number where I squared is equal to minus 1. Verify that Z can be written as 1 minus the square root of 3i. So show that this is equal to this. Okay, so we're starting off by writing out what we're given. Z is equal to 4 over 1 plus root 3i. And generally speaking, we don't like the fact that it's dividing by a complex number. So how do we deal with dividing by a complex number? We multiply both the top and the bottom of the fraction by the conjugate of the bottom. So the conjugate of the bottom here is when we change the sign of the imaginary part. So I'm going to multiply by top and bottom by the conjugate of the bottom. And the reason I'm allowed to do that is because I'm effectively just multiplying by the number 1. 1 can be written as anything over itself. Minus 3i all over 1 minus square root 3i. Okay, so I'm really just multiplying by the number 1. How do I multiply fractions then? I multiply fractions by top, bottom by bottom. So 4 by 1 is 4. 4 by minus root 3i is minus 4 root 3i. And then when multiplying a complex number by its conjugate, there's a lovely little shortcut. Okay, if you remember this rule, multiplying any complex number by its conjugate, it ends up just being a squared plus b squared. So it's 1 squared plus the square root of 3 squared. The square root of 3 squared is just 3. So we get 4 on the bottom line, and then 4 divides into 4 once. 4 divides into minus 4 root 3i minus root 3i times, and then that's the question done when we get down to here. Next part of it says plot Z on an Argand diagram and write it in polar form. Okay, so roughly speaking, the square root of 3 is 1.73. So I knew it was 1 minus the square root of 3i. So I knew it was 1 on the real axis. I just needed to sort of visualize what the square root of 3 was on the imaginary axis. I also know that I want to write it in polar form. So I need or, the modulus, and theta, the argument. And remember, theta, the argument, is the angle that the complex number makes with the real sense of the positive sense of the real axis. So it's this angle here that it forms, that big angle outside here. But that big angle is quite difficult to find. It looks like it's smaller than 360 degrees, and I know 2 pi is equal to 360 degrees. So it's going to be this orange angle, and take that orange angle away from 2 pi because we like to deal with radians here. So it's 2 pi minus that orange angle, and the orange angle is the reference angle in this case. So we can get the reference angle by drawing in a triangle, a right angle triangle. And we know that this length is 1 and this length is root 3, which we can see here. And we know then that r is going to be opposite over adjacent for tan. So tan of r is opposite over adjacent. R is tan inverse root 3 because root 3 over 1 is just root 3. And capital R is 1 over 3 pi radians. Okay, so brilliant. I have the reference angle. Does that help me find theta? Yeah, as I said, we're just going to take it away from 2 pi. So it's 2 pi minus 1 over 3 pi to find our argument, the red angle. Okay, so that's this bit ticked off. We need to find this small r then. Okay, so how do I find that small r? I use the modulus formula. Use the modulus formula. A and B coming from the complex number in rectangular form, and we're getting the modulus to be 2. That's simple enough. And finishing it off by just subbing it back into this formula here. So 1 minus the square root of 3i is the same as 2 cos 5 pi over 3 plus I sine 5 pi over 3. And that's that question done. The next part of the question is a bit trickier. It's a bit of, if I was going to describe it, it's a bit of a strange question, to be honest. We're going back a while now, 2013, so I do find the further you go back, the stranger the questions are. So I used the Modulus theorem to show that z to the power of 10 is equal to this thing here. Okay, well, this was z, and so was this, and we're going to put it to the power of 10. So we want to use the Modulus theorem. The Modulus theorem, so put it to the power of 10. The Modulus theorem says that it's the modulus to the power. So it's going to be 2 to the power of 10, and then the argument by the power. So modulus to the power, argument by the power. Now, because we want to show it's 2 to the power of minus 9. Because we want to show it's minus 2 to the power of 9, I'm probably not going to multiply this out. I'm just going to leave that 2 to the power of 10 there. I'm going to multiply the 10 by the 5 pi over 3 to get 50 pi over 3. And I'm going to continue to go and multiply cos of 50 pi over 3 out into the calculator. Stick that into the calculator, stick that into the calculator, and it gets you that minus a half and root 3 over 2. So somehow I need to link this line of maths here and this line of maths here. Start by worrying about what's the relationship between this and this. I'm going to change it to, so it's 2 to the power of 10 is equal to, it's not equal to minus 2 to the power of 9. They're not equal, that's fine. How could I make them equal? I would have to multiply this guy by minus 2. Minus by minus is plus. Minus by minus is plus. 2 to the power of 9 by 2 to the power of 10. 2 to the power of 9 by 2 to the power of 1 is 2 to the power of 10. So I could rewrite this as this. And I don't need to put in the power of 1 because, look, 2 to the power of anything. Or 2 to the power of 1 can just be written as the 2. Okay, so that's what I do here. That's explaining that bit here. And in the next part, I'm multiplying in by that minus 2. Minus by minus is plus. Minus 2 by minus a half is 1. Minus by plus is minus. Minus 2 by root 3 over 2 is minus root 3, which is what they asked us to prove, and that's it. QED question done. In general, A, B, and C are really nice at this question, and all the way, and C up to here. C up to here, I think, is nice. Hopefully, if anything ever comes up like this again, this will jog your memory and you'll have seen something like it. Hopefully, you found the video useful.